Yeah, I kind of just right now, I decided to abandon chapter 11 because I think we've learned everything you need to learn for chapter 11 and begin chapter 10 because chapter 10 is something you really need for math 11 if you're taking math 11. And then once we are done with chapter 10, I'm going to go back to 11:10 and cover one one more thing. Excuse me. I have a cough button. And cover one more thing from chapter 11, which is on Taylor polynomials and finding value of a, like let's say, square root, or finding value of a natural log, or sine or cosine. So we'll begin chapter 10. Okay, I want to cover enough section from chapter 10 so that you can take your next test soon enough. And then towards the end, we'll go back and do section 11:10. So let me show you what you're dealing with in chapter 10. Really cool stuff. I'm going to share my screen here. I'll be sharing a different screen. See, okay. Yeah, so Wolfram Alpha. And I'm gonna copy a bunch of equation and paste in here. So these are what's called parametric plots. Okay, these are equations that give you graphs that are not a typical function of x, meaning that you can come up with y equal to f of x that would generate these graphs. The equations are fairly simple, but the graph, well, you'll see. So that's one graph. I think it's a butterfly. It's supposed to be a butterfly. And these are equations. Okay, so this is called, again, a parametric plot. And these are called parametric equations. And I hope you guys can see that. And again, this graph, no way, this graph is a function of x. Okay, but again, these equations are not that bad. Okay, and they generate such graph. Here's the next one. I'm running 10 different things at the same time on here. Oh, that's the same thing. Okay, give me a moment. Okay, look at that. I don't even know how or who came up with these equations, but man, that kind of looks cool. But again, look at those equations. Not that bad at all. And they generate this type of graph called a parametric graph. Next one. Isn't that crazy? And look at those equations. So these equations, we have x and y. As you notice, x and y are both functions of a third variable, t. T happens to be the independent variable. X and Y are dependent variables. Okay, so this is not like before where you have one independent variable and one dependent variable. Here we have one independent variable T and two dependent variables X and Y. I think the next one is supposed to be Batman. I honestly don't know who came up with these, like how they designed them. I don't know. Like someone probably, well, here we have those are basically waves getting bigger in amplitude, I guess. But T here is called random equations. They probably do put in like random equations and something comes out of it. But here we call T is called a parameter. Okay, T in the independent variable is called a parameter. And again, those are called parametric equations. Okay, so this is my least favorite one. Yeah, and let me just send you these equations. You can maybe send this one to your boyfriend, girlfriend, loved one. Okay, in the chat. Yeah, we are gonna do polar graphs. When we do polar graphs, we're gonna generate something like what you see here. It's called a cardioid. The polar form of this is a lot easier to graph, and that will be in section 10.2. So you sometimes can think of T here as time. If this is the motion of a particle in the XY plane, T can be thought of as time. So when you change T, every T corresponds to a point on this curve, okay? Or AT corresponds to a point XY on this curve. So for different values of T or time, you get different XYs on the curve or on the plane that is called a parametric curve. The set of points XY, parametric curve. So this is used a lot in motion. And that's why I said you guys are going to do this in Math 11, because Math 11 is about motion, curves in space, work, the amount of work that is done by a force field to move a point from A to B on a curve, on a parametric curve, which is a function of time. Yeah. So really cool stuff. A lot of you, if you're taking Math 11, you are definitely going to enjoy Math 11. I promise you that. All right. So let's talk about it. Of course, we are not going to be learning how to graph exactly those equations because I don't even know how to graph them. You basically need a software. So section 10.1 is on the basics of parametric equations and parametric graphs. Section 10.2 is on the calculus of those equations, and as well as arc length and surface area of revolution. Section 10.2 is going to be a long section. Section 10.3 is on about a certain type of a parametric curve called a polar curve. And then 10.4 is on the area. It's about area of polar functions. Okay, so if you try to describe the motion of a, let's say, a particle that travels on a certain curve, like let's say we have this curve. Okay, this is a parabolic trajectory. This is the x-axis, this is the y-axis. So x is the horizontal direction, y is the vertical direction. The equation of this path is basically quadratic. It's a quadratic function, y equal to ax squared plus bx plus c. Okay, which basically relates x and y. It relates the horizontal, I guess the horizontal displacement or distance, or I don't know what you want to call it, to the vertical displacement. Yeah, displacement. Okay, it relates directions, I guess. Okay, relates x and y. But this equation has, there's absence of information, okay, in this equation. This equation doesn't, one major problem with it is that it doesn't tell you which way the particle is moving. That's one problem with it, okay? So it describes the relation between x and y, okay, in the movement assuming that, again, this is supposed to describe the path of a particle, but we cannot tell which direction the particle is traveling. Okay, we don't know if the particle is going that way. We don't know if it's going this way. That's it. So not good, really. So what we want to do, there's basically absence of time in this equation. Okay, so what we want to do is describe, if you are doing physics, you want to describe position, which is xy, and this is in R2, it's in the plane, okay? With respect to time. Okay, which means that we want x and y to be functions of time. Okay, again, if you're doing physics. All right, so you want basically the input, we want a certain type of a function where the input is t, which is an element of reals. By the way, someone might say, okay, how can t be a real number? Because How could t be any real number? Because t is time and time is always positive or non-negative. Well, t, it doesn't have to be, okay? This doesn't have to be about motion. T doesn't have to be time. T could be just, you could generate a curve and t could be anything. So that curve could represent anything. It doesn't have to be motion. So t could be a real number. And again, if we are talking about motion, t has to be a positive or non-negative number. And we want the outputs. Output here is weird. Again, output is not y. Before input was x, output was y. But here the output is xy, point xy, which is an element of R2. Well, R2 is the two-dimensional space, okay? When you go to math 11, this will be x, y, z. It's an element of the 3, R3, the three-dimensional real space. And they make it a little better in math 11. They do this using vectors, okay? So you have like a vector valued function. You have a function, you have a vector that is a function of time, function of t. But here we just keep it as output is just a set of points in R2. Okay, and good time to define what a parametric curve is. Again, a parametric curve. So here I said t is time, and well, t could be time, okay? Yeah, t could be time. And if it's time, then you're describing motion. But if t is anything, then you're generating a curve. Okay, that curve again is a path of a particle if t is positive, if you're applying it to motion. But again, that path or the curve is called a parametric curve. Yeah, is a set of a graph or a curve is a set of points x, y in the plane or in R2 such that x is some function of t. I'm not calling it time, okay? It's just t. And y is some other function of t, okay? Where these functions f and g are continuous on t interval I. So we are interested in parametric curves whose equations is continuous. Okay, yeah. So I continuous on an interval I, on a t interval I, and here we call these equations x equal to f of t and y equal to g of t parametric equations. With t being the parameter. The independent variable t here is called the parameter. Okay? And we saw a bunch of parametric equations. You saw them. X is some function of t, y is some function of t. All right. So let's do examples, graphing a few of these equations, simple versions of them, okay? We're not gonna be graphing anything crazy for now. The hardest that we'll graph, if we have time, will be something like this. This type of a curve. All right. So example. This is how I write my parametric equations. C here stands. So here C means curve. Okay. So here I say C, the curve is described by x equal to t and y equal to square root of t. Okay, and of course, here we have a square root of t. We want t to be non-negative. This is the interval, t greater or equal than 0. Okay, so this could be motion of a particle. It could be. Okay, but it generates a curve, and we want to just graph that curve. So you know how you began graphing back in like 3rd, 4th grade? I don't know what grade you guys started graphing. You always graph, you learn graphing by plotting points, right? And then later you did like library of functions. You learn about the shape of different graphs. And then you learn about transformation rules. You transform, you shift the graphs. You shifted a parent function to graph the function. And then later you did some analysis, algebraic analysis, like in pre-calculus, sign analysis, to see if one graph is below or above. And then in calculus, you did derivative analysis. So as time goes on, the methods got more advanced and more advanced. Okay, but here we're gonna have to advance in a couple of days. Okay, we're gonna start by plotting points, and then later we're gonna discuss calculus. Ahmed, this is the same t. This t, when we say t is greater or equal than 0, that t applies to both of these t's. Yeah. Yes, this t is the same as this t. Okay, we have only one independent variable or one parameter, but we could choose values for t here to determine x and y plot points. Before you chose values for x to determine y, well, we're not doing that here anymore. So the table that you're gonna form is gonna have 3 columns, the t column, and then we have the x column and the y values. Okay, so let's choose values for t. I'm gonna begin with 0. When t is 0, well, x is the same as t, so x is 0 and y is square root of 0. That's also 0. Okay, let's choose 1 for t. When t is 1, x is 1, and y is square root of 1. That's also 1. Okay, you can choose 2 for t, but then y is going to be square root of 2, and I don't want to deal with that. So I'm going to choose a perfect square like 4. Yeah, you don't have to. You could choose 4. It's easy. T is going to x is going to be 4, and y is square root of 4, which is 2. Okay, let's just choose one more point. Say 9, which is a perfect square. X is going to be 9, and Y is going to be square root of 9, which is 3. Okay, so we have enough. Now, we are going to graph this curve. By definition, the curve is the set of points x, y in R2. There is no t when you graph. There is no t-axis. So this is just, again, a graph in the xy plane and nothing else. We are not in the three-dimensional space. T is not a dimension, or T is not a spatial variable. It's just, it's just acting as a parameter here. Okay, so we have only a y-axis and a t-axis and an x-axis. So here our first point is 0, 0, 0, 0 is, let me do that in a different color. Right there, right there. And what you can do, you don't have to do this, you can label this as the point corresponding to t equals 0. Okay, you can. Let me just number this axis. Yeah. Next point is at 1, 1. Okay, so at this point, scaling of x to y is not 1 to 1, but no one cares. 1, 1, this corresponds to t equal 1. Okay, next point is at 4, 2. 4, 2. Right there. This is corresponding to t equal to 4. Okay, and then we have 9, 9, 3. Right there, corresponding to t equal 9. Okay, those are just labels. And here we have a half parabola. Okay, yeah, half parabola. Now, this is a parametric curve, and it is incomplete. This curve, as is incomplete because it's not indicating direction. We need to indicate the direction of the curve, or also known as the orientation of the curve. Orientation is basically the direction of the curve as t increases. Okay, so as t goes from 0 to 1, we're going from this point to this point, so this way. Okay, from 1 to 4, we're going this way. We're just going that way. What is that? North, east direction. Okay, we need those arrows, guys. Those arrows are a part of the curve. They must be drawn. You don't need to do the labeling. Okay, you don't need to do that, but the arrows are a must. The arrows tell you the orientation. Okay, and if this is motion, then that would be direction. The orientation of the curve is the direction. Of the curve as t increases. Okay, so again, t, if it was time, time is not something that you can graph. It's not a point, but this is basically the representation of time. Okay, the orientation. Yeah. Okay, any questions? A half parabola graph. You know what you can sometimes do, if possible, you can eliminate the parameter t, because we are familiar with a relationship, an equation or a relationship between x and y. If someone gives you y equal to x squared, you can immediately graph that. Okay. Yeah. The question is, can we describe this curve as a relationship between x and y, as an equation between x and y? And the answer is yes, if you can eliminate the parameter. Okay. Eliminating the parameter t is you coming up with an equation that relates x and y. Yeah. We may be able sometimes be able to come up with an equation relating x and y by eliminating the parameter. So I'm saying sometimes because sometimes the algebra is going to be so difficult or impossible that you can't eliminate t to describe x in terms of y or y in terms of x. But for these equations, the process is really, really easy. Okay, we can easily eliminate the parameter for this equation, these equations. All right, so for example, here again, we know that x is just equal to t. Okay, and y is square root of t. Well, t is the same as x, so substitute that. You get square root of x. Okay, relation between x and y is y equals square root of x, where here x is of course greater than 0 because t is greater than 0. So, well, we got y equal to root x. We all know that the graph of y equal to root x is exactly that. Okay, so sometimes if you can eliminate the parameter, do so that you don't need to plot point. You won't have the need to plot points. Okay, but this is the non-parametric version of the curve. Okay. What is bad about this is that it doesn't tell us the orientation. It doesn't. Okay, we need the actual equations to know which way. So you can eliminate the parameter graph. You do this first, graph it, and then plot a couple of points in the equations to see which way. Okay, if this is like, let's say your first point and this is your second point, then we know it's going that way. Well, let's do more advanced equations. And again, section 10.2, we'll learn about the calculus of these. We'll do a direction analysis, which tells us which way, that way or that way. We'll be analyzing derivatives of x and y in section 10.2. Next example, and please stop me if you have questions, guys. C is defined by x equal to t minus 1, y is t squared minus 1. And here we are told that t is between -1 and 3, including the endpoints. Yeah, here t could be negative. Who cares? This is still gonna generate a curve. Okay, so again, you can eliminate the parameter first, or you can just plot points, whichever you're comfortable with. Sometimes people eliminate the parameter and they can't identify what they're dealing with. Okay, especially if you're dealing with a sideways parabola. But let's just plot points. Okay, so I got to begin with -1. We'll do -1. Just take all points in between, all integers in between. 2, and then we'll take 3 endpoints. Okay, so when t is -1, you get -1 minus 1, which is -2. And y is going to be -1 squared minus 1. That is going to be 0. -1 squared is 1. You plug 0 in, you get -1 for x, and then 0 here, you get -1 for y. Yeah, choose 1. 1 here gives you 0. 1 in here gives you also 0. Okay, 2 minus 1 is 1. And here 2 squared minus 1, 4 minus 1, that's 3. And then here we have a 3. 3 minus 1 is 2. 3 squared minus 1 is 8. 2, 8 is the other endpoint. Yeah, let me just number my axes. Again, the ratio of my x to y is not 1. The x units seem to be bigger than y units. It's not preferred that you do that, but I mean, there's nothing wrong with it. First point, -2, 0. -2, 0 is here. Okay, and again, you can label these points. You don't have to. You can label them, I would suggest, because it helps you with the orientation. Okay, -1, -1, the second point right there. And that corresponds to t of t of 0. Yes, 0. Okay, and then we have the point 0, 0 right there, corresponding to t equal 1. We have 1, 3. T is equal to 2. And then we have 3. We have 2 and 8, corresponding to t of 3. Okay, so here we get an arc of a parabola. How come I'm not reaching that point? I don't know why I'm not reaching. Let's see. 2, 8. This happens when your numbering is not really good. Okay, so we have 1, 3, and then 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. Right. And we stop right there. Okay, this curve doesn't continue. It's closed. This is a closed curve. Okay, t starts at -1 and stops at 3. So yeah, arc of a parabola. Okay, so the parabola, the full parabola would have been like that. Okay, it's an arc of it. And we all see the orientation. It's a counterclockwise orientation. Okay, going from one endpoint to another endpoint. Again, need those arrows, guys. Okay, let's eliminate the parameter and see if we can identify the function. Again, you can begin by eliminating the parameter. Okay, so a tiny amount of algebra is going to go into this. Take either of the two equations and solve it for t. We are trying to eliminate t. So solve one equation for t and plug it into another equation. Okay, so let's take this equation. Yeah, this is given that you can solve for t. Sometimes we can't. Yeah, so first equation is easier. We have x equal to t minus 1. Okay, which gives us t equal to x plus 1. Okay, and substitute into the other equation. Okay, the other equation is y equal to t squared minus 1. Okay, which becomes x plus 1 is t squared minus 1. Okay, so the non-parametric form is y equal to x plus 1 squared minus 1, which is again a parabola. It's a quadratic function. It's a parabola. It's opening upward because the leading coefficient is positive, and the vertex is at -1, -1. This is shifted 1 unit left and 1 unit down, which is exactly what we have right here. Okay. Yeah. -1, -1. But again, bad thing about this equation is that it doesn't tell you anything about the orientation of your curve. Okay. No questions? Wolfram Alpha, when you graph these on software, it doesn't do orientation for you, by the way. You have to code that in. Next example, you are gonna be seeing these parametric equations a lot. especially in math 11, multivariable calculus. So our curve C is defined by x equal to a cosine of t, y equal to a sine t. Your famous functions, where t here goes from 0 to 2 pi. This is a closed curve. Oh, did I say the previous curve is closed? I meant to say, I did not mean to say that. This is not a closed curve. Can anyone tell us what this curve, what is this curve? Thank you, Jose. Remember that day, guys? I was covering some hyperbolic functions. I mentioned this also yesterday. Where is it? Hyperbolic functions. Yeah. I began by section 6-7. My handwriting was a little better back then. Not so good, but looks a little better here. These are circular functions. Yep. X equal to cosine t, y equal to sine t. Guess what? Back then we did parametric equations and you didn't know. Here t is any real number, but look at those circular functions, okay? Because they satisfy the equation of a circle. Okay, you can think of t in this case as the angle. But well, let's see. So you can again plot points here, which would be 100% fine, or do exactly what Jose said. Okay, let's eliminate the parameters, because once the functions become ugly, well, this is not ugly. These are beautiful, actually. I don't want to sound like a nerd, but it's just the relation between x and y is so apparent. Oh, by the way, let me mention here that a has to be positive. Yeah. So once the equations get more complex, then you want to begin by doing some analysis on them before plotting points. Honestly, plotting points should be a last resort, because plotting points doesn't always give you a universal picture of the graph. Okay, so let's begin by eliminating t. Okay, so the rule, the algebraic rule, is that solve one equation for t and stick it into the other equation. That is the algebraic rule. But guys, this is not algebra. These are trigonometric functions. You don't want to do algebra. You don't want to solve for t. I've seen people taking that and dividing x by a, and then taking cosine inverse of that to solve for t, and then they plug that into here and they get like a sine of cosine inverse of x over a, which means nothing. I mean, like, and they leave it at that. How is that supposed to make the problem easier? So not a lot of times you have to do algebra, or not always you have to do algebra. Okay, here we have trigonometric functions, cosine and sine. So look for an identity that relates your trigonometric functions, because guess what? An identity is an equation. It's an equation that is always true. That identity is going to give you a relation between x and y. Okay? So here, when trig is involved, okay, use an identity relating the two involved trig functions. Okay, cosine and sine, so cosine squared plus sine squared is equal to 1 is the identity that you have to use. Okay, so use cosine squared t plus sine squared t equal to 1. This is the identity that we have to use. So you look at your equations and you see a cosine, you see a sine. Solve for those and plug them into the identity. Okay. So what do you want to do? You want to solve, Ahmed wants to solve for A and make him equal. Then you have an equation that has cosine, sine, x, and y. How's that gonna help you? Maybe, I don't know. You can try it out, but this is a lot easier. We have this identity, we have the components of the identity sitting right there in front of you. Okay? Yeah, so here from the equations, the parametric equations, we have cosine of t equal to x over a. That's why a had to be positive. A can't be 0. So solve that for cosine t. Solve this for sine t. Sine t is y over a. And plug into the identity. Okay, so cosine of t is x over a. And we're squaring that. Plus sine of t, y over a. Square that, and the identity says it's equal to 1. The audio is bad. Let's see why. Oh. Can you guys hear me well, or does it sound glitchy?
Sounds fine for me.
Fine. Yeah, maybe it's your speaker, Nick. Okay, so there we go. We have a relation between x and y. You can just clean this up a little bit. You have x squared over a squared plus y squared over a squared. Multiply everything by a squared, and yeah, I'll just write it down. So yeah, you get x squared plus y squared equal to a squared. Okay, so this is the non-parametric relationship between x and y. Okay, which is a circle. This is the equation for a circle centered at 0 with radius a, centered at the origin with radius a. Okay, that's what that equation is for. All right. Yeah, and then we know how to graph that. We just need to know the orientation, so you could just plug a few points. Okay, let's just do that. Let's graph. Okay, so Again, we're gonna choose a few values for t, not a lot, to see what x and y are. Okay, so again, x is a cosine, y is a sine t. Let's just choose easy values like 0 for t. Okay, so here we get a cosine of 0. Cosine of 0 is 1, so a times 1 is a, and then sine of 0 is 0. And at the same time, I'm going to graph. Okay, let me graph the circle first, and then, and then because I'm going to have such a hard time graphing. Okay, good enough. So A0 is this point right here. Okay, so assume that from here to here is A, and this corresponds to t of 0. Okay, so imagine A is 1. Okay, so that point is 1. Okay, and then if I choose pi over 2 for t, I'm choosing something like pi over 2 because I have cosine and sine involved. It's easy to find cosine of pi over 2. Cosine of pi over 2 is 0, so x is 0. Sine of pi over 2 is 1, so you get a times 1, that's a. A0 is, or 0a is this point. Say that corresponds to t equal pi over 2. Okay, so t here is acting as the angle. Okay, you can think of it as if it's time, let's say t is time, but it also geometrically is the angle whose terminal side falls on, whose terminal side contains the point on the circle. Okay, we can choose pi or any number in between, who cares? Cosine of pi is -1, you get -a. Sine is 0, -a0 is here, that corresponds to t of pi. We can choose 3 pi over 2. Cosine is 0, sine is negative. That point. And then 2 pi gives you a 0 back. Cosine of 2 pi is 1, so you get a times 1, sine of it is 0. So this point is corresponding to t equal to 2 pi as well. Obviously, the orientation is counterclockwise. Okay, from 0 to pi over 2, we are going from this point to that point. Okay, this is the orientation. Counterclockwise. We call the counterclockwise orientation the positive orientation. Counterclockwise is positive, clockwise is called a negative orientation. You're going to learn about that in Math 11 in more details. Okay, but these equations, you can do a lot with them. You know, the relationship between x and y, the non-parametric relationship, is algebraically difficult to deal with. You know, if you're like, let's say, finding the circumference of the circle or the arc length, let's say, you don't want to do calculus on the xy form. We want to do calculus with the parametric form. It's a lot easier. It's as if you're doing a trig substitution, you know. And we're going to do all of that later. Okay, so I am gonna close with a definition. I have like a few minutes and I want you to think about it. This is about a what's called a simple curve, a very, very important definition when you're doing what's called differential geometry. A simple curve Okay, so we say that a curve C is set to be a simple okay. Don't be confused by that word. That word doesn't mean easy. Okay, a simple curve is a curve that doesn't intersect itself. Okay, yes, that's what a simple curve is. It doesn't intersect itself. And of course, I have to write this out mathematically. Okay, every definition has a mathematical representation. Let's look at a curve that is not simple. Guys, please pay attention because later we're going to do some algebra and you need to really understand the definition. This is a circle is called a closed simple curve. Okay, this is a closed circle, a closed simple curve. Unless t goes from like 0 to 3 pi where it overlaps. Like let's say you're going around the circle twice, then it's not simple anymore. But as is, this curve is closed, simple. So it is simple, okay? This is an example of a non-simple curve. So imagine this is motion, okay? Some particles traveling on this path. Okay, let's just say at some point, this is a non-simple curve, okay? The particle's going this way, let's say, and at some point, at some time, let's say at t1 is equal to u. The curve is at this point P. So let's say after 1 second, the particle's here, okay? So this position corresponds to t of like, let's say u. All right, and then the particle is gonna travel for some time, and then it's gonna, let's say, after some later time, it's gonna meet this point P again. Okay, so this is happening, let's say. Okay, so that point is corresponding to some later time v. Okay, so let's say after 1 second, t equal to 1 point is here, and then that point is, let's say, 3 seconds later. Okay, this curve is not a simple curve because of course it's intersecting itself. Okay, so a curve that is not simple, a non-simple curve means that simple if for two different time values, for u different than v, we get x at u equal to x at v. The x values are the same, and y at u is equal to y at v. This is saying you get the same point. You get the same xy at two different t values. When this happens, curve is not simple. Okay? Yeah, we'll see examples tomorrow. But think about this definition, please. Two different t values give you the same XY, give you the same position. Okay. Right. I think Jose got it. Before I wrote down the definition. Yeah, we are done. This is essentially, this is something you guys learn in pre-calculus, actually. This definition is the definition of a I want you to think of the non-parametric form of this from algebra. What kind of function would this function be in algebra? It's okay, I'll just tell you. Not a one-to-one function, yes. A non-simple curve is not one-to-one. A simple curve is one-to-one. Think about it. Think about it. Okay. All right, I'll see you guys tomorrow. Be here tomorrow. We're going to be doing important stuff.
Thank you.
Have a great day.